don't understand you're saying it's south, it should be south, whatever. Now you know with the development of aviation, it's obvious. You look at the trajectories to go, say, from Paris to New York. It has to be this way, you know. It's a curved trajectory. And we know it's the best way. It looks as a curve, it looks as a path which is not economic on the plane in 2 dimensions. But if you think of it as a sphere, it makes sense. It's obvious that's the way it should be. So spherical geometry, in a sense, is more simple than plane geometry for that reason. On the other hand, plane geometry is more economical because you just use 2 dimensions. While spherical geometry, you need the 3 dimensions, you know, to put your sphere in something, in our space, which is 3-dimensional. So it seems that it demands more information, the sphere. So this is the kind of dilemma that you have. Either work on a simple geometry that requires many dimensions, in this case many 3, or work with a complicated geometry that requires few dimensions, in this case few is 2. This is a problem that can get much more complicated than this, but this is the essence of this problem, which the geometers call embedding. Embedding is like the spherical representation because we think of the sphere as part of the 3-dimensional space, as embedded in the 3-dimensional space. And on the contrary, the plane representation, geometers would call it intrinsic, because it only uses the 2 dimensions which are intrinsic to the surface of the sphere. So, intrinsic or embedded. What is geometry? Should it be intrinsic or should it be embedded? It takes us back to the problem of what we want to do in geometry. At first, geometry developed, you know, with the ancient Greeks as the Euclidean geometry, doing figures that you can draw in the sand or on paper or on the flat stone or whatever. But then people understood when you travel long distances and so on, you need to understand spherical geometry. And then some people say, after all, you could do geometry on any surface, not especially a sphere. It could be some weird thing. And then people said, let's work on any possible geometry and devise a theory that can encompass all of them. And let's try also to do things which withstand deformation, things which are as intrinsic as possible. You know, if you take a sheet of paper and you make a drawing on your sheet of paper. This is my sheet of paper, I do some drawing on it. If I bend the sheet of paper, from an embedding point of view, it will be very different. But the figure here will remain the same. So if I look at it intrinsically, it should be the same object. And geometry made huge progress when it started to think intrinsic terms, even for curved geometries. This is related to the development of the Euclidean geometries in the 19th century, and in particular the so-called hyperbolic geometry, which was devised by people like Gauss, Lobachevsky. Hyperbolic geometry, like the Euclidean geometry, was a geometry in which all points were equivalent, no privileged point. A sphere also is such a geometry, you know. On a sphere, from any point, the sphere looks just the same. There are very few geometries which have this property of looking the same. And the hyperbolic geometry is one like this. But somehow it's the inverse of the sphere. While the sphere is always positively curved, the hyperbolic plane is always negatively curved. And it has some weird property. Here is an example of the picture in the hyperbolic plane. And it was proven by some of the famous mathematicians of 20th century. Hilbert, for instance, who said it's impossible to have a very large hyperbolic crochet. So, okay, this seems like, yes, the embedded geometry is restricted. And there are some geometries like the hyperbolic space that we cannot embed. No. Then the mathematician will tell you, okay, we cannot embed it in our three-dimensional space. But who said we need three dimensions? Let's dream. Let's embed it in a space of 4 dimensions maybe, or 5 or 6, whatever. It was proven by Blanusa that you can embed the hyperbolic geometry infinitely large in a 6-dimensional space. So in the end, it is embedded geometry all the same. But we just needed to enlarge the point of view. And now you may say, is it the same for any geometry? So here's the rule. I give you an abstract geometry, an abstract surface for instance. Can you find a Euclidean space, a straight space, but possibly with 10 or 20 or 100 dimensions, in which I can embed my geometry, such that it will be a part of the geometry, as the sphere is part of the three-dimensional geometry. And this was a problem that stood open ever since the time of Riemann. An old respectable problem. Now, let's go back to Nash. I have to understand that Nash was not very humble as a young man. Nash was rather, annoying. And when he arrived in MIT, one of his colleagues, Ambrose, quite good mathematician, became so annoyed with Nash's arrogance, like, oh, I'm a genius, I'm the best in here. Okay, winner is good, but I think I'm even better, and so on. And once he was so angry, he told him, if you're so good, why don't you solve the isometric embedding problem? Nash's reaction was, what? What is this embedding problem? What is this about? Nash was like thrilled. Oh, is this a difficult problem? Maybe I can become famous by solving it? Okay. Asking people whether this is really a problem that can make him famous. Starts working on it. Spends more than years on it. Wow. He said, I will solve it, etc. Here is my idea, here is this, and so on. Ambrose laughs at him. We have a letter of Ambrose in which he says to one of his colleagues, there's Nash, we've got him. And we saved ourselves the possibility of having gotten a real mathematician. He's a bright guy, but conceited as hell, childish as winner, hasty as X, obstreperous as Y, for arbitrary X and Y. This is mathematician humor, Okay. But now the thing is, Nash did solve the problem. Not only one proof, but two amazing proofs, two amazing theorems that he got from it. Non-smooth embedding, smooth embedding. People were not even aware there was an interesting non-smooth embedding here. He proved both. Let me explain a little bit what it was about. First amazement was the method of proof. It was an abstract geometry question, you see, general question. When you have a general question in math, natural to think it will be solved by general reasoning. Abstract question will be solved by actual proof. Not at all. Solved it by getting his dirty hands to big calculations, and we'll get back to that. It was to anticipate a little bit the same amazement as when Russian genius Gregory Perelman solved the most famous Poincare conjecture about all possible shapes of dimensional universe, a very general question, hands on and technical calculations and reasonings. Of Nash's proof, Gromov said, first works which made Riemannian geometry simple, an incredible change of attitude on how to think of manifolds, to manipulate them. This leads us to the question, what is an analyst? We ask the question, what is geometry? Now what is analysis? Mathematicians is not a single species. You have several, or rather you have several subspecies, subspecies and so on. analysis can be compared to fine QC. Japanese is the same word, by the way. It needs fine-tuning, control, analysts pride themselves on the strength and sharpness of contact with simple and powerful tools. They like to study in great detail functions, signals, often unknowns because they are solutions of problems, and they ask how fast they change. Is it a small variation, a fast variation, a big variation? Like stock exchange, will it fluctuate very much or so on, etc. Some examples of functions. Some of them are smooth, slowly, others are wild, and so on. And they spend their life on this. But the main first tool of analysis are the derivatives, the differentials. This is the speed of variation. This is the slope. And the inventors of this famously were Newton and Leibniz, who were both geniuses and engaged in a horrible battle for the shame of mathematical community in a sense. But it was brilliant what they did. You know, look at this graph there. If I draw the tangent to the graph, which is the curve which is the line which touches the graph, and I look at the slope of this line, it will tell me instantly what is the variation, if it's growing fast or decreasing, and so on. And when I have this slope, I can, for any value of the variable, plot the value of the slope, and then look at the slope of the slope, which is the variation of the variation, the second derivative, and so on. And I can continue. The study of these successive derivatives gives me strong information about the way these functions change. This is what people call regularity. Derivative is easy to understand. You know, 1% interest rate, we understand this easily. Second derivative, not so easy. Starting from third derivative, it's really difficult to get it. Well, actually, there is a famous example of third derivative in political speech. This was Nixon, 1972, when he announced publicly that the rate of increase of inflation had started to decrease, which, as you may guess, was not such a great news, you know, and which, as you see, was a good way to say things are improving in a way that nobody can understand. But for analysts, it's no problem. We're used to this. We use arbitrary numbers of derivatives, or dimensions, for that matter. Even fractional number of derivatives is no problem. And the more derivatives there are, the more the function is smooth. This is our daily bread, and it can change the conclusion of a problem. For instance, if you're looking at a problem about fluid mechanics, whether you're looking for smooth solutions or non-smooth solutions, it will change not only the mathematical attack, but the physical conclusion of the problem, and so on. And as a true analyst, Sash revealed that in that geometric problem, the regularity was very important. And depending whether you're looking for a smooth embedding or a non-smooth embedding, the answer will be completely different. Geometers had no idea about this. The proofs were incredible. For instance, to construct his smooth embedding, Nash started by grossly reducing distances, you know, a way that was certainly not an embedding, and increasing them back progressively by some progressive process by spiraling, not like crazy idea. And from the smooth embedding, he attacked an incredibly difficult system of equations. Solutions, in a sense, loses derivatives. Let me not say anything about this, except that it was identified as a nightmare. And he understood that you can counteract this nightmare by a numerical method which had been devised by Newton to solve equations in a very, very fast way. In one problem, it's a regularity issue. In the other, it's like a numerical problem, finding solution. But he understood he could play one against the other. Nobody had a clue about this. the methods were founding, and the tools that he introduced gave rise to new theories, which later would be taught, you know, in mathematical classes, even without referring to the geometric problems that had been introduced to. It was not only solving problems, but finding new techniques to solve these problems. And the conclusions were powerful and amazing. Here's another thing that Gromov referred to as impossible. You may take a sphere and crunch it without altering its geometry, its intrinsic geometry. Neither getting bumps, you know, not like taking a hammer and back. There will be no bumps, still it will be crunched. This is contradicting our experience. We know in some sense that the sphere is rigid, but that transforms the fact experience because it is hardly smooth. Here is how it looks like. This is the way that Nash, or rather, this is how a few years ago a team of mathematicians represented what Nash had proved to exist. A way to embed the flat torus. What is a flat torus? It's a geometry that is well known to people of a certain age who used to play Pac-Man. You know Pac-Man? It's like a square, and there is some labyrinth, whatever, and there is your Pac-Man, your body, and it goes, and when it goes out in some direction, it enters back through the other side, you know. And when it goes this direction and gets over the top, it comes back from the bottom. This is known to mathematicians as the flat torus geometry. A geometry in which you identify left side and right side, and up with the down. And that geometry, if you try to do it on a piece of paper, okay, let's identify this with this, easy. I do like this. Okay, and I glue this. Indeed, if my little guy will go there, it will enter the other side, etc. But now you try to glue this to that. Does not work, and you can prove it doesn't work. Well, Nash tell you, my friend, it doesn't work if you go for a smooth embedding. But if you do it in a clever way, and that is the clever way, it works. So that thing here, which nowadays is called a smooth fractal, looks like this. You see how it has tiny structures and microstructures and microstructures and so on. Still, it's not irregular as a fractal. There is a derivative at every place in there. And it is flat. If you are a tiny microscopic being living on the surface of this, you would not distinguish, you would not feel that it is curved, for it would be perfectly flat. It took years before geometers digested these new things of Nash. Came 2 years later, the great embedding system. If you take an abstract geometry, you may embed it in a very smooth manner, so than this, but provided you put enough dimensions. In this, you only needed 3 dimensions. Make it in 3 dimensions, but you can do it in a large enough number of dimensions. This was great achievement. And here, problem which had been asked something like 80 years before, whether the point of view of Gauss, Bendit, and the point of view of Riemann, intrinsic, were actually equivalent. Answer, they are. That was good. That was good, and as a result of this, Nash had demonstrated that he mastered regularity better than anyone. That's the reason why Louis Nirenberg, when he saw Nash arriving in quantum physics, that's the guy to solve my problem. It was for a problem of regularity of partial differential equations. Partial differential equations. Partial differential equations are equations about derivatives, tangents. But in real life, a function doesn't depend on one variable. It depends on many variables. Take temperature, for instance. If you're interested in meteorology, it just depends on the time No, this morning it was quite cold, today it's better, and so on. Depends on the latitude, on the longitude. Depends on 4 parameters. So you may compute the derivative with respect to any of these parameters. Is it getting warmer by the minute or colder by the minute? Is it getting warmer when I get to the south, etc.? Partial derivatives capture this. The tendencies with respect to the parameters. And it's the big discovery of people starting from the 80th century that almost any phenomenon you can think of eventually is modeled by these partial differential equations, related the tendencies of the function. For instance, temperature in this room, it's a problem of partial differential equations. Electric potential in our brain, it's a problem of partial differential equations. Control understanding the motion of fluids, it's partial differential equations, etc. Here are some of the most famous partial differential equations. I don't want you to understand them, but first, you may appreciate how beautiful they are. This is Boltzmann equation. Gosh, I spent 10 years of my life on this. This describes the evolution of a gas. Was first devised by James Clerk Maxwell and Ludwig Boltzmann, and changed the face of theoretical physics. This here set of equations tells us about the evolution of a galaxy, for instance, over billions of years. This one, on the contrary, is so small. Schrödinger equation, the basis of quantum mechanics. This one actually, when you go to Paris, you may visit a public place in which it is engraved. It's in the Paris subway. Sculpture in the Station Châtelet-Léal. I like it because every day probably hundreds of thousands of people pass near this without noticing whatsoever that there is a Schrödinger equation there. You know, like a metaphor of the fact that we are surrounded by these marvelous equations around us without us noticing this. Here is another couple ones. These are the equations of fluid mechanics. Euler equation, Navier-Stokes equation. They changed everything in our technology, or many things. They are solved every day to predict the weather. They are used at enormous length by the Hollywood industry to make all kinds of special effects in the movie theaters. The Titanic or whatever, it's full of resolutions of these partial differential equations of fluid mechanics. Okay. And here's another one which was solved by other mathematical genius Alan Turing to understand the problems of pattern formation on the skins of animals. And here is another one which was used by Joseph Fourier in the 19th century to understand the temperature, say in a block of iron. Here it is, heat equation. It's a famous partial differential equation, and when you take courses in partial differential equations, one of the first that you study. It's about temperature in a block of metal. Starting. On the left is the time derivative. Tendency of the temperature with respect to time, getting warmer or colder. And on the right, there is a space derivative and actually two space derivatives. Tendency of the tendency with respect to the spatial variable. And there is a coefficient C, the conductivity, or to be more rigorous, thermal diffusivity. They are in relation to each other. Because you know, in some materials the heat is easy to transmit, in some others difficult to transmit. When you have a conductivity that changes from place, say in a mixture of two metals, the distribution of heat can become quite complicated. The equation is complicated and the solution too. You cannot compute it exactly then, but you can study it. Let me show you some examples. Here's an example in which you have a heat distribution in a metal bar. Hot, cold, hot, cold. You see this is X. This is like the distance to the origin. And initially you heat some places and see how it evolves with time. You let it cool down. Look carefully. This is the evolution of temperature as time goes. At the beginning I had several bumps. Now I only have one. It's getting a bit boring because the evolution at first was very fast and now it's very slow. That's one of the first things that we learn when we study heat equation. Fast and then becomes slow. Other things that we learn is that even if globally it's cooling down, some places are cooling down, others are not. Initially, look at this hot spot and this cold spot. After just a moment, the hot spot is becoming cold, but the cold spot is becoming warm, until there is some kind of equilibration, and then they start to get decreasing. Okay. Another thing that we learn in these courses is that heat equation regularizes things. It makes you smoother. Look here. Is it smooth? Well, not much. You see these strong variations, wide variations of the slope. Changes completely. But look, after a fraction of a second, it has this smooth. You know, as a mountain gets eroded, heat equation shows some kind of erosion of the data. This is a regularizing effect of the heat equation. Okay. This simulation here is for a constant, a homogeneous metal bar. Let's now look at another one in which it would be a mixture of various metals. To start with an initial data of temperature that is crazy, you know, hot, cold, completely crazy. Look what happens after a few seconds. Smooth but better. And you know, here it was quite discontinuous, but here continue and better and better. It's not as irregular as it was with the homogeneous metal bar, but still not so bad. Had some regularization effect. At least that was the conjecture. And that is exactly what Nirenberg wanted Nash to do with mathematics. Take any alloy, you know, any mixture of metals, in any geometry, in any dimension, and any distribution of heat initially, and let it act for a few seconds. Will it become good? It may seem like a very specific problem, but this was an important problem because it was a key problem to understand a whole class of relating. And Nash, how to do this? Okay. That is what I was just explaining to you. And this is the mathematical statement. So if temperature of M and X is the heat distribution in a medium with discontinuous conductivity, you know, any mixture, and the discontinuous initial distribution of temperature, after 1 second, will the temperature be continuous? This is the problem. And Nash is very interested, also checks that he can become famous for this, and starts working on this. Starts working on this, gets started and works on the problem. It's fascinating because accounts and testimonies on how he worked on it. Going and meeting the people, you know, getting back to Nirenberg, tell me more about it, I want to know this, and is it true that this and that and that? Nash was not a specialist at all of that, of mathematical physics, diffusion equation, here. And then he went to see other people in Princeton, people in New York. Hey, I heard that you are a specialist of this, can you explain me this, that and that? And at first his questions are quite stupid, you know, like he was an outsider, not knowing about this, and Nirenberg was starting to wonder, hey, is this guy as smart as they said? And little by little, questions were becoming more and more to the point. And he was putting everybody to contribution as a conductor, you know. Hey, my friend, need you to prove me this and this. I think that you are the expert and you can give me this. I can use it to prove something more and so on. As a conductor who would give assignments, you know, here you are the violin player, you will play this and this. You are the trumpet, you will play this and this. Each one does their part. Nobody understands the great plan except when the orchestra starts to play. And Nash had the overall plan for this. And everybody was amazed when after 6 months the program was moved, putting all people to contributions. And again, the solution was amazing. Let's examine this famous paper that he wrote from there. One of the most famous papers in the 20th century partial differential equations. Continuity of solutions of and elliptic equations by John Nash. And now you understand what it was about. 1958, 24 pages, rather short. By current standards, very short. It's interesting to read what he thought. His open problems in the area of nonlinear partial differential equations are very relevant to applied mathematics and science as a whole. Perhaps more so than the open problems in any other area of mathematics, and this field seems poised for rapid development. It seems clear, however, that fresh methods must be employed. We hope the paper contributes significantly in this way and also that the new methods used in our previous paper will be of value. That was absolutely true. Little is known about the existence, uniqueness, and smoothness of solutions of the general equations of flow of a viscous, compressible, and heat-conducting fluid. It's still true. Almost 50 years after what he wrote, we are still in the dark about some basic features about this. The style was formal and informal.